Your knee joint is hiding a secret organ that has never once touched a drop of your blood, and almost nobody realizes it. Right now, inside your cartilage, there are cells older than most of your other tissues, quietly working without a single blood vessel to feed them. They survive on leftovers, on diffusion, on a slow trickle of nutrients drifting through fluid instead of racing through arteries like everywhere else. And for decades, these cells have relied on one hidden internal system just to stay alive and functional. That system is called autophagy, your body's built-in recycling machine, and it might explain more about your joints than you think. So what actually happens when that recycling machine gets triggered again and again for 30 straight days? The answer connects to a mechanism most people have never once linked to their aching knees or stiff fingers. Cartilage is one of the strangest tissues in your entire body, unlike almost anything else you carry inside you. While your muscles, your skin, and most organs are fed directly by a dense web of blood vessels, cartilage gets nothing at all. It is officially classified as avascular, meaning there is no internal blood supply reaching it whatsoever. Oxygen and nutrients have to slowly diffuse through synovial fluid before they ever reach the cells inside. This isn't a design flaw, it's actually a brilliant structural choice made by evolution itself. Cartilage constantly absorbs compression, shear, and repeated mechanical stress every single time a joint moves. A dense network of fragile blood vessels simply could not survive that kind of relentless daily pressure. But this clever design comes with a serious hidden trade-off nobody warns you about. Without direct blood flow, cartilage cannot access the rapid repair systems other tissues take for granted. Its survival depends almost entirely on the handful of cells living quietly inside it. And that dependency is exactly why autophagy becomes so critically important here. In tissues rich with blood flow, damaged material often gets cleared through circulating immune cell support. In cartilage, the internal recycling systems of its own cells carry nearly the entire burden alone. Understanding what happens to that recycling system becomes the foundation for everything you're about to learn. Inside cartilage, there's essentially only one type of cell doing all the heavy lifting, the chondrocyte. Unlike skin or muscle, which use multiple cell types working together as a team, cartilage relies almost completely on chondrocytes to build, repair, and maintain everything around them. These cells continuously produce and renew the protein scaffold that gives cartilage its shape and strength. Chondrocytes are famous among researchers for dividing incredibly slowly compared to almost every other cell type. In mature cartilage, chondrocyte turnover is remarkably low, and existing cells often remain for decades. This extraordinary longevity means each chondrocyte must manage internal damage for an entire lifetime without easy replacement. There's no backup team waiting nearby to swap in fresh cells whenever something goes wrong. This is precisely why autophagy carries so much weight, specifically at the chondrocyte level. Research has repeatedly linked autophagic activity in chondrocytes to maintaining long-term cartilage stability and structural balance. Multiple studies show that when this process becomes disrupted, cartilage degeneration tends to follow soon after. Because these cells cannot simply be replaced quickly, their internal quality control system becomes absolutely essential for survival. Autophagy alone often determines whether cartilage stays healthy or slowly begins breaking down over time. When a person stops eating, the entire body doesn't respond to fasting in exactly the same way everywhere. Early fasting signals like declining insulin, activated AMPK, and reduced mTOR activity spread throughout the body. These signals reach nearly every cell you have, including chondrocytes buried deep inside your joint cartilage. In tissues with strong blood supply, these fasting signals arrive quickly and trigger fast metabolic shifts almost immediately. In cartilage, because nutrients travel slowly through diffusion instead of direct circulation, everything happens on a noticeable delay. The same systemic fasting signals likely reach chondrocytes much later than they reach more vascularized tissues elsewhere. This delay doesn't mean nothing is happening early in the fasting process at all. Autophagy has been described as a major regulator of chondrocyte survival and overall cartilage matrix stability. The same upstream cellular signals that trigger autophagy elsewhere in the body exist here too. What actually differs isn't whether the mechanism exists, but how quickly it responds inside cartilage. And that timing difference becomes far more relevant once fasting extends beyond just a few hours. As your body ages, the relationship between cartilage and autophagy begins shifting in a measurable, documented way. Research comparing chondrocytes from younger versus older cartilage consistently finds lower levels of key autophagy markers. Proteins like ULK1, Beclin-1, and LC3 appear noticeably reduced in aging or arthritic joint tissue. This pattern was documented clearly by researchers studying both human and mouse cartilage samples extensively. Their work showed autophagy capacity in chondrocytes declines progressively with age, often years before visible damage. The cells are essentially losing their cleanup machinery long before your joints ever show outward signs of wear. This decline doesn't happen randomly or without a clear underlying biological cause driving it forward. One of the central regulators involved is the mTOR pathway, the same nutrient-sensing system controlling autophagy everywhere else. In chondrocytes specifically, rising mTOR activity actively suppresses the formation of protein complexes needed for autophagy. This effectively shuts down the cell's own internal recycling and cleanup machinery when it's needed most. Counterbalancing mTOR is AMPK, an energy-sensing enzyme that activates autophagy whenever cellular energy runs low. Multiple independent studies have identified mTOR as the primary inhibitor and AMPK as the primary activator, and this critical balance between the two pathways appears to shift unfavorably as cartilage tissue ages. The scale tips increasingly towards suppression rather than activation as the years continue passing by. The consequence of that shift is anything but abstract or purely theoretical for your joints. When autophagy declines, damaged mitochondria, misfolded proteins, and oxidized molecules begin accumulating inside chondrocytes instead. Because cartilage cannot recruit fresh replacement cells, this damage stays localized and steadily builds cell by cell. Several research groups have described this slow buildup as a major contributing factor in age-related degeneration. This distinguishes it clearly from injury-related cartilage damage, which tends to follow a much faster timeline. Osteoarthritis has traditionally been described simply as mechanical wear accumulating after decades of joints absorbing constant impact. But the age-related decline in chondrocyte autophagy raises a much sharper and more uncomfortable question. If the cleanup system is already weakening naturally with age, is osteoarthritis really just mechanical wear? Or is it partly a failure of cellular maintenance that happens to appear mostly in older joints? Research over the past 2 decades has increasingly pushed toward that second, more complicated interpretation entirely. Scientists are now treating osteoarthritis less as simple wear and more as shared cellular dysfunction. This finding matters enormously because it reframes osteoarthritis as something far more than passive, unavoidable aging damage. If autophagy is actively suppressed in diseased cartilage, structural breakdown isn't purely mechanical anymore at all. It becomes the downstream result of a maintenance system failing to keep pace with accumulating cellular damage. Supporting this idea, animal studies have shown that experimentally enhancing autophagy in chondrocytes reduces degeneration markers significantly. Meanwhile, models where autophagy genes are knocked out consistently show accelerated, faster cartilage breakdown across the board. These remain associative and interventional findings drawn primarily from animal and cell culture research so far. Researchers have been careful to note the field is still working out human translation carefully. What has become much clearer is the specific molecular chain connecting reduced autophagy to actual tissue breakdown. Studies show low autophagy activity correlates strongly with higher levels of enzymes called matrix metalloproteinases. These enzymes break down the collagen and proteoglycans that give cartilage its essential structural integrity. In healthy tissue with strong autophagic turnover, this breakdown stays balanced through ongoing natural repair processes. When autophagy falls, that delicate balance tips sharply toward degradation instead of maintenance and recovery. This relationship has been described repeatedly across independent experimental models by researchers working in this exact field. Cartilage never functions completely alone inside your joint, no matter how isolated it might seem. It sits bathed in synovial fluid, the thick liquid filling your joint capsule and serving two purposes simultaneously. It lubricates surfaces so they glide smoothly and delivers nutrients cartilage cannot receive through blood vessels. This fluid comes from the synovial membrane, the thin tissue lining your joint capsule from the inside. Its composition is closely tied to the overall health of your entire joint environment. The synovial membrane itself contains cells that depend heavily on autophagy for their own survival. Researchers increasingly study the synovium alongside cartilage now, rather than treating them as separate, unrelated systems. In osteoarthritic joints, the synovial membrane frequently shows signs of persistent, low-grade chronic inflammation building over time. Inflamed synovial tissue releases inflammatory molecules directly into the synovial fluid surrounding your cartilage constantly. Because chondrocytes depend on that exact fluid for nutrients, changes don't stay contained within the membrane. They reach the cartilage too, creating a dangerous feedback loop between two connected, dependent tissues. This is where autophagy's role becomes especially layered and important across both tissue types simultaneously. Healthy autophagic activity in synovial cells helps regulate how much inflammatory signaling gets released into joints. Meanwhile, autophagy in chondrocytes determine how well those cells withstand whatever inflammatory exposure does occur. When both systems function properly, the joint environment tends to stay stable with lower inflammation overall. When autophagy declines in either tissue, synovial fluid composition shifts toward a more inflammatory, less protective state. This relationship has been documented primarily in laboratory and animal model research, rather than direct human trials. Inflammation inside a joint is never a single uniform event happening all at once suddenly. It involves immune cells, signaling proteins called cytokines, and cascades that resolve quickly or persist for years. One of the most studied cytokines in joint research is interleukin-1 beta, often shortened to IL-1B. This molecule is strongly associated with both acute joint injury and chronic long-term osteoarthritis progression. Laboratory studies show IL-1B directly suppresses autophagy in chondrocytes, lowering their ability to clear damaged components. This happens at exactly the moment when that cellular clearance matters most for joint health. This creates a genuinely vicious cycle that feeds itself over and over without outside intervention. Inflammation increases IL-1B levels, which suppresses chondrocyte autophagy, which then allows damaged components to accumulate further. That accumulation, in several experimental models, has been linked to further activation of inflammatory pathways inside cells. This can amplify the original inflammatory signal, sustaining or even worsening it over extended periods of time. Researchers studying this loop suggest it partially explains why joint inflammation can become self-perpetuating once established, though this specific work remains concentrated in cell culture and rodent models with limited human confirmation. Autophagy's relationship to inflammation isn't limited to chondrocytes simply reacting passively to outside inflammatory signals either. Several studies have found autophagy itself influences how much inflammatory material gets released from cells initially. This dual role, being both affected by inflammation and capable of regulating it, is fascinating scientifically. It's part of why autophagy draws so much research attention specifically within joint disease studies. One of the most direct demonstrations of autophagy's role came from a landmark study published years ago. Researchers led by Beatriz Karames induced osteoarthritis in 2-month-old mice through surgical knee joint destabilization procedures. Half the group received rapamycin, a compound known to inhibit mTOR and activate autophagy pathways directly. The other half received a vehicle control with absolutely no active treatment or intervention applied whatsoever. After 10 weeks, mice treated with rapamycin showed measurably less cartilage degradation than the untreated control group. They also showed lower histological damage scores alongside clear evidence of increased autophagy markers throughout their tissue. This finding mattered enormously because it moved the relationship from simple correlation towards something closer to actual causation. It wasn't just that healthier cartilage happened to show more autophagy activity by pure coincidence alone. Deliberately increasing autophagy through pharmacological means produced a measurable, undeniable protective effect on joint tissue. A separate study published in 2014 took this discovery one step further using a different genetic approach. Researchers genetically deleted mTOR specifically within cartilage tissue in mice, which itself increased autophagy naturally. This reduced the severity of experimental osteoarthritis significantly, reinforcing that this pathway was a genuine driver. Human research in this specific area remains far more limited than the extensive animal work conducted so far. Directly manipulating autophagy inside living human joint tissue raises serious ethical and technical obstacles researchers must navigate carefully. What human studies have consistently shown, using cartilage samples from joint replacement surgeries, mirrors the animal findings closely. Chondrocytes from osteoarthritic and aged human cartilage display noticeably lower autophagy markers compared to younger, healthier tissue samples. The mouse studies established a plausible causal mechanism worth taking seriously across the scientific community. The human tissue studies confirmed that same biological signature appears consistently in actual living patients too, even though establishing direct causation in humans, the way researchers established it in mice, remains genuinely difficult. If you've made it this far, you now understand something most people never learn about their own bodies. The cartilage holding your knees, hips, and hands together depends entirely on a hidden cellular recycling system. Translating laboratory findings into a specific 30-day window requires real scientific caution before drawing firm conclusions. Most controlled research on autophagy and cartilage comes from continuous pharmacological activation studied carefully inside laboratory mice, not from repeated daily fasting-induced autophagy studied in humans across an entire month-long period. That distinction genuinely matters and deserves honest acknowledgement before describing what existing science actually seems to suggest. Fasting-induced autophagy and rapamycin-induced autophagy activate overlapping but not entirely identical biological pathways inside cells. Both converge on mTOR inhibition, but they operate through completely different upstream triggers and likely different magnitudes. With that important caveat clearly in place, available evidence still points toward a few plausible structural changes possible if autophagy were meaningfully and repeatedly activated inside joint tissue continuously over an entire month-long period. Based on mechanisms described in the rapamycin studies, sustained activation would likely support continued clearance of damaged mitochondria. This could potentially slow the kind of intracellular debris accumulation strongly associated with natural cartilage aging processes. Matrix metalloproteinase activity linked to extracellular matrix breakdown might also shift favorably given documented relationships in experimental animal models. What current science genuinely cannot yet specify is the precise dose-response relationship required specifically for humans. Nobody yet knows exactly how many days of activation are needed before measurable structural changes actually appear, or how daily fasting-induced autophagy compares in raw magnitude to pharmacological activation used inside those mouse studies, or whether 30 days represents any meaningful biological threshold versus a much longer or shorter necessary timeline. Cartilage's famously slow turnover, the very feature making its cells vulnerable to long-term damage, cuts both ways here. It likely means any structural remodeling from increased autophagy would unfold gradually rather than producing dramatic sudden shifts. That gap between what the mechanism predicts and what's actually been measured points to something larger and important. For all the genuine progress made mapping autophagy's role in cartilage, several major unresolved questions still clearly remain. The relationship between autophagy and osteoarthritis has been shown predominantly through animal models and single-time-point human tissue samples. What's largely missing is longitudinal human data tracking the same individuals across months or years continuously over time. Studies that could finally establish whether changes in autophagy actually predict changes in cartilage afterward, rather than the two simply appearing together within a single isolated snapshot moment during surgery. There's also an unresolved question surrounding dosage and timing specific to fasting, rather than pharmacological intervention entirely. Nearly all the strongest causal evidence for autophagy's protective effect comes from rapamycin administered continuously over many weeks, not from the kind of intermittent, nutrient-driven autophagy activation associated with periodic human fasting practices instead. Researchers in this field remain genuinely cautious about extrapolating findings from one biological trigger directly onto another, since intensity, duration, and cellular targeting of autophagy can differ substantially depending entirely on what activates it. Finally, the relationship between autophagy and joint aging appears far more complicated than a simple more equals better model. Some research suggests excessive or poorly regulated autophagy under certain conditions can itself become associated with chondrocyte stress. Which means the actual goal in ongoing research isn't maximizing autophagy indiscriminately at every possible opportunity available. It's understanding the specific conditions under which autophagy genuinely supports cartilage health versus tipping into imbalance instead. That nuance, more than any single isolated finding, represents exactly where the current science honestly stands today. A mechanism with real, demonstrated relevance to joint health, studied carefully enough now to be taken seriously, but not yet mapped completely enough to answer every single question a curious mind might have. The next time your knees ache after a long day, remember what's actually happening deep inside them. A quiet, ancient recycling system, working without blood, without backup, keeping you moving for decades longer than expected.